Hello, welcome to a quick demo of PC Crash. I'm going to show the steps that you take towards solving a collision, and I'll talk about the vehicle models and the collision models just briefly. So you can see we have something already set up here. We have a background image that shows vehicles colliding and coming to rest and some skid marks. We've already loaded some vehicles. There's a vehicle database. Default for North America is the Canadian specs database. The European database and some Asian databases are also included as part of PC Crash. So you'll see if you pick a vehicle from the database, you can see the parameters that are included in that database. Pretty sparse on the North American side, but it has just the general geometry of the vehicle and a bit of inertial parameters. So a vehicle is modeled as a rigid body. If I look at the vehicle settings, you'll see that vehicles have a mass, length, width, height. The wheels are in different positions. There are moments of inertia, center of gravity, height. And then various suspension properties, stiffness and damping at each wheel. You can specify the occupant's cargo separately from the vehicle mass or include it in the mass as you like. There's different tire models you can use. Change some of the wheel properties. And you can attach trailers to vehicles too. So you'd load in the vehicles by either loading a vehicle and then modifying it or creating your own vehicle. Anything that's going to collide is vehicle in PC Crash. And PC Crash's impact model is an impulse-based model. So what you want to do is position the vehicles at their maximum engagement. So I'm going to drag these guys in so that they're on the tire marks that they're leaving. There we are. So about like that. And then we're going to find impact parameters and speeds that result in motions matching the kind of post-impact velocities or post-impact positions that we've documented, and these trajectories getting to those positions. Now, the PC Crash will solve the equations of motion in discrete time steps. So you see the default for just running a vehicular simulation would be about 5 milliseconds for the integration step. You can step that down to check for convergence if needed. So tire forces, gravity, suspension forces are calculated at for every vehicle state, and then the vehicle motions are integrated over that time step. Collisions occur between time steps. So what you do there is, if we look at the crash window, you have vehicle speed specified, and then you specify a point of impact. So let me just pick some starting speeds for the vehicle, move the point of impact over here. So this is a single point in space and time where the collision forces are being exchanged. There's a closed form solution to the magnitude and direction of the impulse that will result in a common velocity between the vehicles at that point of impact, given their linear and angular velocities and where that point of impact is, and their inertial parameters. And then you can constrain that to, there's an inter-vehicle friction coefficient here. So let's say there's more sliding between the vehicles. You'll see that impulse direction there, that blue arrow, will change depending on the available friction between the vehicles. And that's, the effective friction coefficient if you compare the normal force of impact to the tangential force. So if there's a full non-sliding impact, large friction coefficient is fine. It's not going to make a difference. So I'll just do a crash here, and there's an option to have automatic calculation of secondary impacts. I'm just going to turn that off for the time being. So if I do a crash and just simulate the vehicles out to rest, maybe I'll fill in the vehicles so that it shows up a little bit more. you'll see the vehicles just drive right through each other. It's going to turn off last position. There we go. This is because the tire forces for the struck vehicle, the blue vehicle, result in the end of its lateral motion, but the striking vehicle continues moving forward. So what we need is another impact. So we could, if we want, do that. We could just specify a second impact here. If I toggle those vehicle shapes again, you can see that point of impact. Then you can specify the contact plane angle. So you see that the vehicles are moving at closer to the same speed, so we have a much lower impulse here. And if I simulate again from there, so we got another little kick, a bit more lateral velocity, but not enough. So PC Crash has a way you can automatically specify, you can automatically detect crashes and automatically apply impacts. So if I run it from here, there you can see it did a number of discrete little impacts. So that's just a way of modeling sustained contact by a series of discrete impulses. So you can see that we don't have enough velocity to reach these rest positions. So if I increase the speed of the striking vehicle, you see that it increases the amount of the impulse. All right, now we're going something like the right distance, but it looks like 2 should have some more speed too to have us come to the right rest position. Looks like this vehicle needs to rotate a little more. Number 1. So we just pull it over. So you can see I'm adjusting the speeds and the impact parameters in order to find rest positions that match and trajectories that match the data that we have. So this process can continue, but you see I'm already got something kind of close, and now I'm just making some finer adjustments. So PC Crash has a tool called the Collision Optimizer, where I can specify the rest positions for the vehicles, drag little ghost images of the vehicles out, and then the algorithm has a way to measure how close its solution is to the actual event. So if I go to the Collision Optimizer, I say what parameters I want to vary, and then run the optimizer. So now you can see it's varying all these parameters and showing the results of each calculation. And the percentage shown there is the cost function there, the difference between the calculated rest position and the rest positions I specified. And in parentheses, it shows the best trajectory error thus far. There we are. So you can see that this set of impact parameters resulted in a pretty close set of vehicle motions. You'll see the little lines it's drawing to show where the tires go match pretty closely to where the tires actually went. And they come to the right kind of rest positions. So it's found us with 31 and 30 kilometer per hour impact speeds. And then I can go into my values window and look at some of the parameters it calculated. So for the primary impact there, I can get the velocity changes, and that's the vector velocity change. I can get the total deformation energy, which is the change in the kinetic energy of the system before and after, including rotational terms. And I can get my principal direction of force from that primary impact. expressed in the SAE coordinate system. So that's the rough idea of how PC Crash calculates things. You'll notice this isn't a closed form solution for impact speeds given impact positions and rest positions and friction parameters. This is a time forward simulation. It's calculating the forces acting on each object independently. It's integrating the effect of those forces on that object over a small time interval, and then repeating, recalculating the forces and reintegrating. And then impacts occur between those time steps. Momentum gets exchanged instantaneously between objects if there's a collision, and then the trajectory simulation carries on. You'll see on pccrash.com we've got a lot of videos up showing different other features of the program, showing how you can have fancier looking vehicles for display, how you can animate your collisions, use of point clouds, use of 3D road geometry, all kinds of different features that PC Crash supports. So take a look at the videos over at pccrash.com and see the other features that PC Crash can give you for your analysis, so you can find what happened in a given collision.